Hello everyone. In this presentation we'll walk through the software architecture of VFE module. The prerequisite for this session is an understanding of Camera 2 overview. I may be using a few terms specific to the architecture, so I highly recommend you to go through the architecture, Camera 2 architecture, before starting on this tutorial. Before we go into the details, let's have a look at the topics that we will cover today. We will start with a brief overview of the VFE4 hardware architecture. Just to note the terminology VFE4 and ISP, we use these terms interchangeably. When you hear the term VFE, it's same as ISP. Once we cover the hardware architecture detail, we will move on to an overview of the software picture. This is a brief diagram, small diagram which explains the different components inside the ISP module or the VFE module and the interactions of this module with the module before that. It will also have some details on the threading model, the different layers inside and so on. Once that is covered, we will get started with the initialization part. This is also known as the module init. What it essentially means is the system initialization. What happens during system initialization and what happens inside ISP during this initialization session. Once we cover the initialization part, we move on to what is known as the session init or camera specific initialization. So when a front camera opens or a back camera opens, what really happens inside the ISP module. ISP software module to be precise. Once we cover that details, we move on to the stream specific details. As you might know from the hardware the overview, Camera 2 architecture can support multiple concurrent sessions and multiple concurrent streams. As I just explained, sessions means a front camera or a back camera, and within a front camera or back camera there could be multiple streams running at the same time. These streams could be a capture stream or a preview stream or a video stream. These are independent data pipes that is running in ISP. So what happens when a new stream is created? So those are covered in the caps reserve and the stream config presentations. The slides here. Once we cover those details, we move on to the stream on. That's a bigger part. Most of the ISP specific initializations happens during the stream on part. We'll cover the details on what specific modules, sub-modules or the sub layers get invoked and what happens within the different data structures within ISP. These are the main topics that we will really touch upon today. And these are the most important aspect of the ISP or the VFE module as well. We'll briefly also talk through on the threading models, how many threads exist and what's the functionality of the threads, and may peek into the source code as well. We'll also cover some debug pointers. As I walk through the source code in this presentation, I'll specifically highlight the functions which enable you to debug the source code. And under miscellaneous topics, we will also cover what happens during dual VFE, Zoom session, and so on. And at the end of the presentation, there's a link to further questions. Let's get started with the hardware picture. The VFE4 hardware has, I would say, 3 or 4 different parts. There is a front end, as you can see, the gray box which is connected to the CSID inputs. This module mostly deals with the bare processing. So if you step back and look at the hardware architecture, ISP or VFE gets input, raw bare data inputs from sensors. It converts the raw data to RGB or YUV data and generates one or multiple, mostly 2 outputs. Along with generating the processed output, which could be YUV or RGB, it also has capability to generate various statistics. The statistics could be based on the data that is processed in the Bayer domain, or could be based on data which is processed in the RGB domain. So if you look at the diagram here, you would see the gray box, which is the Bayer processing. The blue box is the histogram, is the statistics processing, which gets input from the Bayer processing blocks and also get input from the YUV or RGB processing block. And what you see, the purple box down here is the YUV RGB processing pipeline, and at the end, the orange box deals with the output of ISP. And output of ISP deals with the scaling and also the color conversion, required color conversions. Let's move on to the software architecture part. Two main parts of ISP is an ISPIF or I-phase module, which deals with the input of ISP pipe. If you look at the input of ISP, you would see CAMIF interface part, which deals with the CSID. The I-phase module abstracts out these interactions, and there is not much of software or the stream-specific processing that happens in I-phase module. The majority of the bulk of the software processing happens within the module called ISP module here. Now the input to ISP module, as expected, comes from the I-phase module. So you could see an input coming here, and the output of ISP module could be connected to either a post-processing module, the data output goes to a post-processing module, or the statistics data that is generated from the stats module, as you would have seen in the previous diagram, goes to the 3A specific module, which gets the statistics data and do a 3A processing. Now inside, now zooming into the ISP module, you would see data structures specific to each session. If you step back and look at overall architecture, ISP or the Camera 2 architecture can support multiple concurrent sessions. For each session, ISP module creates a specific data structure. That's a high-level abstraction. Now, within the session-specific data structures, ISP manages multiple streams. These streams could be considered as a copy of the user streams that comes into ISP, but it has its own internal data structure which is tuned towards ISP processing. Now, for every stream, ISP also maintains what is known as a channel data structure. We'll cover the details as we browse to the source code a little bit later. And to deal with the buffer management abstractions, input buffers and output buffer, ISP has what is known as a buffer manager. The buffer manager deals with getting the buffers from the HAL, that is the camera HAL interface layer, or it also allocates buffer if ISP needs to do an internal buffer allocation. At the lowest level of ISP software is the ISP hardware interaction modules, which deals with AXI configuration and also with input pipeline configurations, the pixel configurations. The other point to note here is the interaction with the actual hardware. The interaction with the actual hardware is abstracted as a V4L2 subdevice, and what you see or what we cover mostly in this presentation would be the user space configurations. The actual hardware programming happens as a subdevice. These subdevices exist as a V4L2 subdevice, and you would see ioctl calls throughout ISP code, which interacts with the kernel level drivers for hardware configuration. The important point to note is the concept of streams or the concept of sessions is managed pretty much in the user space, and the kernel is mostly a slave to the command that is given from the user space ISP module. Now let's get started with the initialization part. As explained below, the very first initialization that happens is the module init. This gets invoked when the camera comes up, or the camera daemon comes up in the system. And this happens only once, and it doesn't happen once in the sense when the phone or the module phone boots up in the system. So this is the top level creation function of ISP. So there are three things that happens during this initialization part. One, it creates the ports. So it's a port data structure. So there are input ports known as the sync ports, and there are output ports known as the source ports. So it creates a fixed number of input ports and a fixed number of output ports. So in the current version of ISP, you would see 8 sync ports or 8 input ports created as part of module init, and 4 stats port and 10 image source ports created as part of this initialization. The next thing that happens is it queries the hardware, or it goes back to the kernel and gets the details about the ISP capabilities. The software architecture is generic enough to work across various versions of Badger family. So it has to know how many instances of VFE hardware, for example, exist, and what's the version of VFE hardware. And then the software needs to be configured based on the VFE hardware version. All these things happens during the module initialization aspect. Now, based on the module initialization aspect, the ISP populates its capability structure as well. View of what happens during this initialization. Now, the init function is present in a file called module.isp.c, as you could see here. And this is the function module ISP init, which gets invoked during this initialization. Now, as you could see, as part of any other module, there is a module creation step. But what's more important is this ISP create. This is the routine which creates the ISP instance. It creates the ISP, the hardware specific operation functions, ops routines, and also gets the specific capability down from the hardware. And down, you would see this specific routine called ISP port create ports. Let's have a look at this function in a little more details to get a feel for what really happens here. Now, as you could see here, there are 2 parts to this creation of port creation. One is called the ISP create source port, and one is ISP create sync ports here. So you would find, okay, so this is the sync port creation first, and it would create a source port here. Now, this is pretty much a pre-configured. At this point, ISP do not have information regarding the number of streams or the stream configuration. So it's a fixed number of allocation done for both input and output streams. Now let's move on to the session init part. Just to recap, the session initialization happens when a specific camera is open, whether it's a front camera or a back camera, or if there's a third camera, fourth camera. For every camera open, there would be a session initialization. There are 4 things that happens during the session initialization. It initializes the default parameters for the ISP, and the other important aspect is it creates a session specific thread. So this is one of the threads. We'll talk through the session thread architecture a little later, but one thread that's created is a session specific. So every session will have a session specific thread. An ISP also would initialize a buffer manager. As explained in the previous PPT, ISP has buffer manager which handles the HAL buffer or internal buffer. The initialization of the buffer manager happens during the session init. And also, the other important thing that happens during the session init is the zoom initialization. Now, there could be a single VFE, or there could be multiple instances of VFE. The zoom specific parameter, the zoom steps and the configuration required for zoom does happen during this session init. Let's look at the source code to see what really happens from the source code perspective. Let's go to the module ISP. This is where the session init would happen. So the exact routine to look for is module ISP start session. And this is an abstraction over the low-level routine ISP start session. So let's have a look at this function. Now, as you could see, what the very first thing it tries to do is find an empty session data structure. So ISP, during the create phase or module init, it creates a data structure for the max sessions it can support. Now, when a specific session needs to be opened, it tries to find an empty session. It would be capped to the max sessions. In this specific implementation, it's capped to 4 concurrent sessions at this point. Once the session specific data structure is obtained, it will open the zoom specific session. You could find zoom specific initializations happening in this routine. As part of the initialization, it also does the zoom init here. As you could see, the ISP zoom open session, it opens a session and does an initialization of the zoom value. There are other initialization related to, for example, the UV subsampling mode and so on. But the most important part, as we just talked through, is the async task creation here. Every time a new session is created, there will be a async task created to handle the session specific processing. We will cover this task details in a while when we talk through about the threading model in the system. Let's move on to the stream specific configuration. Before I dive into the code, let me spend some time on what really happens during the stream session. There are 2 aspects of stream initialization. One is coupling of multiple streams. If you look at a camera use case, you could have, for example, a video stream and a preview stream running together. The coupling between the streams is what is known as the bundling, the stream bundling. An ISP needs to know which streams are connected together. Now, this information, ISP cannot detect this information, so the HAL needs to send specific information or a specific data, a control configuration to ISP to tell which stream are bundled together. Now, before this bundling information is passed to ISP, what happens is every time a new stream is created, ISP gets a call for what is known as the caps reserve or a capability reserve. During this phase of the processing, ISP reserves a specific input port and a specific output port for the stream that is reserved, a stream which makes a call into the caps reserve function. Let's have a look at the function to get a feel for what really happens here. This happens in ISP port.c routine. So let's have a look at the port ISP.c routine and let's go to the caps reserve. Right. Now, as you could see in the caps reserve function, there are 2 parts of caps reserve. One is the sync port reservation and there is a source port reservation. Now, these happens in 2 different function calls to ISP. So when the MCT module tries to connect the different modules together, it tries to connect the source port of the previous module, in this case would be IFS module, to the sync port of ISP module. So it would get first a call to the sync module. Once that connection is established, it gets the next call for connecting the source port module. In this case, it could be, for example, the stats module of ISP with the stats port of ISP with the input port of a stats module, or it could be the data port of ISP connected to the input port of the pproc module. So they could be, based on the requirement, there could be multiple connections at the source port. Now let's have a look at this particular function to see what really goes inside the reserve sync port function. Now, since reserve sync port happens before the source port, the stream specific data structure is created at this point. So you could, let's have a look at here. So very first thing it does when you ask for a reserve sync port is add a specific stream. Now this stream is an ISP's internal data structure. This is, in one sense, we could consider this as a replica of the HAL stream configuration and copies pretty much all data structure from HAL configurations to ISP's stream configuration. Now once that reservation is done, it creates a stream, internal stream. It links an internal stream to the sync port. Now there are two parts to this linking. First, a reservation of sync port. Now reservation is based on the capability that is passed to ISP module. Every time a new stream connect request comes in, ISP do not create a new sync port. Rather, it looks for the capability structure. So in this case, it could be the capability structure that is passed from the sensor. And if the sensor capability structure matches an existing sync port, it adds the stream or ISP internal stream to this existing sync port. New ports are created, new sync ports are created only if the data structure, that is, for example, if there is a new camera created, or it's connecting to a new stream coming from a different camera and so on. But if the stream is connecting from the same camera, the same sync port data structure is always reused. Now once the sync port is reserved, ISP would get the next call to reserve for a source port. Now this might happen twice based on if a stats module is connected and also a data port is connected out here. Now there is similar logic as the sync port. The ports are not created for every time this API is invoked, but this is created if and only if needed. So in the case of source port, ISP caps the max number of source ports to 2. So if there are more than 2 streams, stream create request comes in, it will actually map the stream to existing source port. And there are some corner cases which is specific to dual VFE and so on, but at an overall, the logic is to create a new source port as long as the number of stream request is less than 2. Let's move on to the next step in the stream configuration, and this is called the stream config. The next step in the stream specific configuration is what is called the stream config. This happens based on an MCT event that ISP receives from iFace. The 3 things that happens here. One, it gets the sensor or the stream specific configuration, and that is copied to the ISP's internal stream configuration. 2, it creates a hardware instance, when I say hardware instance, which handles the low level operations of ISP. And 3, it also makes a decision, or it gets an information regarding whether to use a single or a dual VFE structure. Let's look at the source code to get a feeling of what really happens inside, the steps inside. So the routine that gets invoked for stream config is ISP sync port stream config. As you could see, it's a sync port config because this comes at the input of ISP, and the data is coming from the iFace module. Now let's skip through the initial part where it tries to find the matching stream and so on. The important step is here where you could see the ISP's data structure, stream specific data structure, is copied to the ISP. The ISPIF stream specific data structure is copied to ISP's internal stream data structure. It also gets information regarding whether to use a single VFE or a dual VFE. This comes as a mask, VFE output mask, which ISPIF populates. And once the data structure is copied, it also does what is known as the ISP hardware create part. And let's have a look at this routine to get what really happens during the low-level hardware creation. So it populates. So as mentioned, there could be an instance of, there could be one or multiple instances of hardware. So the initialization step gets a instance of ISP hardware. It could be a VFE1 or a VFE, the VFE0 or VFE1, and the specific routines which handles with the low-level operations are populated in the hardware data structure. And also you could see there is an init routine that's being called, which initializes the low-level ISP hardware structure, and then it returns here. Let's move on to the next part, which is probably the most important step of ISP. This happens, this is called the stream on. This is when the real processing really kickstarts across camera. Now just to step back and explain a little bit further, when a specific channel is started, so when you say this channel refers to the channel concept within the HAL, the various streams which are various various streams gets an stream on notification from the HAL or camera interface layer. The stream on notification first comes to the very first module connected. For example, for a specific stream, a sensor is connected to VFE, which is connected to, say, a pproc module. The stream on would first come to the sensor, which would propagate the stream on message down to ISP before it does its own stream on, and ISP in turn would propagate this message to the next module, that in this case is CPP. Assuming CPP or the pproc is the last module connected, it would finish its own stream on specific initialization and then would notify ISP to start its own stream on part. And once ISP completes its stream on configuration, it notifies back sensor to do sensor specific stream on configuration. In this slide, we will talk through the details of what really happens inside ISP stream on. Now, ISP's stream on is an important function because all data processing really starts from ISP. Sensor data comes through the CAMIF interface of ISP. Then ISP does the processing and generates an output, which through the AXI interface, and notifies the rest of the modules on how to start the data processing. So ISP also controls the information regarding multiple streams. For example, if there is a video stream and there is a preview stream, when to start the processing, the hardware processing for each stream is decided by ISP. Let's walk through the code to get details on what really happens inside. So the API which gets invoked in ISP when it gets a stream on notification is ISP stream on, which in turn invokes the routine called ISP proc stream on. Now, as I mentioned earlier, ISP creates a session-specific thread, and this specific routine ISP proc stream on gets invoked from the session-specific thread. And there are multiple steps involved in the stream on process. The very first thing that ISP does when it gets a stream on is to check if it has received all streams corresponding to the bundled sessions. So just to step back and explain, when there are multiple streams involved, HAL passes an information to ISP, giving an information regarding which streams are bundled together. Bundling here refers to which streams starts together and which streams stops together. So when ISP gets a stream on notification, it needs to wait for the stream on information for all the bundle stream before it can do real processing. Now this particular processing or the info happens in ISP util get streams routine. This routine would look at the stream ID pass from the HAL or which comes to ISP as part of the stream on, and compares that against a mask which has a stream ID for all the bundle streams. If all the bundle streams are not received, it returns a 0, and if all the bundle streams are returned, bundle streams are obtained, it returns a number of streams which needs to be started. The next thing, once it receives all the bundle streams, is it creates a channel for all the streams. So let's take an example where there is a video recording session starting, in which case there is a video stream, there is a preview stream, and there is a snapshot stream. ISP would wait until the stream on happens for all the streams. When it receives a stream on for all the streams, it goes ahead and creates an ISP. If in case the streams are bundled, it waits for all the stream on to happen, and when it receives a stream on for all the streams, it creates a channel for each and every stream here. Channel is an internal data structure, and this is not the HAL or the camera interface channel. This is an internal data structure to capture the stream configuration and also the hardware configurations together, bundle the hardware configuration and the stream configurations together. There are two different kinds of processing that would happen on stream on. One, a case when the ISP is already on. The two, where ISP is off and we're doing a stream on for the very first time. If the ISP is already on, it mostly has to update an existing buffers associated with the stream to ISP and do not have to invoke creation of new channels. So you would see two different processing happening in the code based on whether a session is active or not. Now once a channel is created which captures the stream specific configuration for all the active streams, ISP does a sorting of the channels and selection of the pipelines for the streams. In a nutshell, what really happens here is if say there are n channels, it sorts the different channels together, finds out the maximum configuration for each of the channels or the streams, and since there is only one or two hardware streams that ISP can generate, it picks the top two highest resolution streams and maps every other stream to the top two resolution stream. As part of the select pipeline streams, ISP selects the two streams which has the highest dimension. Dimension is nothing but multiply width and height and see the max number of pixels, and picks the first two streams and delete the channels corresponding to all other streams. So let's assume there are say 10 streams. It's a hypothetical case. It sorts all the streams. In fact, it sorts all the channels because stream data is configured, it's mapped to the channels. Once the sorting is done, all first 2 channels are restored and the remaining 8 channels are deleted. And as far and to map the existing streams to and to retain existing stream configurations, it maps all the streams to the 2 channels that is retained. Now once that step is complete, ISP has information regarding the hardware configuration, in the sense it knows what's the resolutions needed for the first output of VFE and the second output of VFE. The next step as part of the stream on is computing the stripe that each VFE needs to work on. Now it's based on the resolution of the stream or based on the number of sessions, both the VFEs could be on for the same stream. And if both VFEs are on for the same stream, each VFE would work on a part of the stream. So this is one place where you need to look for whether this, in the case of dual VFE, where how the stream configuration, how streams are configured for each VFEs. The configuration is pretty much hard-coded, in the sense it calculates the overhead required, the overlap required in each VFEs. As you could see in this code over here, there is an initial overlap of 128 that is set for each VFEs. That is, each VFE would will have an overlap of 128 pixels between the two. Once the compute stream information is complete, the stream on would move on to the configuring the image buffers required for the stream on configurations. This is mostly handled as part of the buff manager within ISP. And there is a util function which invokes the buff manager to initialize the image buff request. This image buffer could come either from the HAL, for example, if the ISP is the last module in the processing, the buffers, output buffers of ISP comes from the HAL, and the buff manager within ISP gets his buffers and initializes this buffer for the stream mount configuration. There could be a second case where the buffer is an intermediate buffer that ISP needs to work on. In this case, buffer manager would go ahead and create those buffers, ion buffers specifically, and it does the initialization of the data structures. Once the buffer initialization is complete, the next step as part of the stream on is the config for the stream on. This is where ISP does the configuration, for example, whether it's an HFR stream and the slow motion HFR is equivalent to the slow motion, could be 60 FPS or 90 FPS or 120 FPS. ISP does the configuration whether the resampling or the subsampling of the stream required for preview is to be done by ISP or to be done in pproc module is decided in this step. Let's have a look inside this function to get the next level of details, what happens inside the stream configuration. Now there are multiple levels of redirections here, so let's go to the last function here. Now the redirection is required because ISP may be processing on a single VFE or a dual VFE. So you would see a redirection or an abstractions to manage both initialization at the same time. Now as part of the hardware configurations, it invokes the low-level hardware stream configuration. And this mostly to do with whether it is using the pipelines, the low-level pipelines, whether it's this one pipeline usage or a 2 pipelines usage, hardware pipeline usage. Those configurations happens at this specific point. And it also invokes the ISP hardware. It also checks if video stream is enabled, If the video stream is enabled, it also configures the second pipeline of the VFE to generate the video stream. By default, it always generates the preview stream. You would see multiple initialization, the default configurations being invoked and sent to the low-level hardware control operations. These configurations happens as part of a separate thread, and you would see a sent an async message passed to a separate thread within ISP, which deals with the setting the default parameters. Once let's come back to the stream on routine. The next important step as part of the stream on is sending the stream dimensions downstream. The downstream in this case is nothing but configuring the low-level ISP kernel driver regarding the number of streams and the configurations of each streams. This is pretty much close to the last step inside last step of the stream on, where it receives it gets configuration for multiple streams, decides which stream maps to the hardware pipeline, and it does the initialization of the hardware pipeline, and once the initialization step is completed, it sends the information downstream in this specific routine. And just before just after the hardware dimension is sent downstream, ISP also has a configuration, the stream on util specific configuration, which triggers the low-level hardware to send the ISP configuration downstream. And the routines that we should be looking at is the ISP channel util stream on routine. This routine looks at the number of hardware channels configured. As I mentioned, the number of hardware channels could be 1 if the video stream is not on. If the video stream is on, it could be 2, and it passes the information down to the low-level configuration using the subroutines available in this module. Once a stripe info is computed, ISP moves on to request the image buffer. The image, let's go into details of the image buffer request. So the first thing it tries to do is actually request the associated channel for the streams. As we mentioned above, even if there are, say, n streams, there would be at max of 2 channels created for the ISP. So it has to figure out for every stream, for all the streams which are active, which are the 2 channels that are associated with that specific stream. Once a channel information is obtained, ISP invokes an API to request the image buffer associated with the 2 channels. Now let's look at the routine which handles the image buffer for the channel. Now there could be 2 scenarios for the channel buffers. 1, the channel is using the native buffer. 2, channel is using the buffers provided by HAL. In short, what native buffers means is the buffer to which the ISP writes is an intermediate buffer. This is not the buffer that the user of camera 2 allocates, in this case the HAL allocates. It's a buffer that would be request or would be processed, would be used between ISP module and the module following ISP. In most scenarios it would be a pproc module, and the HAL buffers in this scenario would be allocated as an output buffer of pproc. The second scenario is when the buffers are indeed allocated by HAL. One common example could be a ZSL preview scenario where ISP or the camera generates two streams, one stream at a preview resolution and the second stream at the full image resolution. The second stream, which is at the full image resolution, goes directly out of ISP to the HAL. So that particular buffer allocation would come directly from HAL. So you would see a call into util request image buff HAL in that scenario. And for the preview buffers, which is connected to the CPP or the pproc module, would allocated using a native buffer call. Now let's go back to the next steps inside the stream on. So once the buffer allocation or the buffer configuration is completed here, ISP starts the configuration for the specific hardware configuration for the stream on. This is mostly to deal with scenarios like whether subsampling or let's say in the case of a high frame rate, does the ISP generates a stream of two streams of say a lower frame rate or a higher frame rate? Where does the subsampling happen? Does it happen inside ISP or does it happen in the pproc module? That decision is made during the stream configuration. Let's go to the routines to get more details inside the code. And as you could see, the stream config or the hardware stream config has to happen for each of the VFEs based on the use case scenario. So there is a higher level routine, prepare hardware config for stream on, which would invoke the stream on for VFE 0 and VFE 1 as and when required. Let's look at one of this specific function to see what really happens inside the low level stream configuration. Now, the first thing that you would notice is it checks if the recording hint is set. Now the recording hint indicates whether the video stream is on or not. If the video stream is on, it has to configure the second output of ISP. If not, it has to configure only one output of ISP hardware, and then it sends the low level configurations like chromatics configuration is sent down to the hardware. Then it would send the stats configuration, default stats configuration to the low level hardware, and it also does the saved parameter. There's a default set of parameters which are saved, and that setting happens during these configurations. And you would also see configuration specific for DIS or image stabilization. If there is an image stabilization, that specific configuration needs to be sent to 3A. That happens during this stream config. Once the stream config is completed, ISP ISP sends the stream dimensions downstream. So you would find a ISP util hardware stream output dimension downstream routine, which would send the dimension required for the top two streams which ISP configures, or the top two channels that ISP configures. And the last step in this configuration is doing the low level configuration for the stream on. Once output dimensions are passed down, we move on to the low level configuration of ISP. The ISP util stream on would send a message to a specific thread which is responsible for doing the low level configuration of ISP. This happens in the file. This specific routine is present in the file called isp hardware.c. uh, you would see a couple of APIs that gets invoked from ISP util stream on, which eventually will kickstart or invoke this API called hardware ISP hardware process action stream start. Now internally in this routine, what you would see is the configuration update for the one or multiple pipelines that is involved in this stream on. So there are quite a few error checks that you would see at the top. Then what's relevant part here is the starting of the specific interface. The first, it starts the ISP stream start for the pixel interface. So you would see an invocation of ISP pipeline action function. This internally would call into an ioctl, the low-level ioctl, to start at the pixel interface of the ISP. Now once the input, pixel interface is the input of ISP hardware is done, it will also configure the AXI interface. So you would see actually a stream start for the AXI code, which invokes the AXI interface for the ISP. That once these two are done, the stream, you should assume that ISP is in a running state at this point, generating input data at a continuous as a continuous mode. The last part of ISP stream on routine is configuring the updating the user streams. It would change the state of every user streams associated to an active state. So let's so that concludes the stream on. So once the stream on routine is completed, the ISP would start generating the data, and there would be callbacks coming in from ISP hardware, which is invoked as part of as a last step and as part of the ISP stream on. ISP updates the stream state for all the active stream to ISP stream state active, and then returns. At this point, ISP is up and running and generating data continuously. Once the data is generated by the hardware, the kernel module gets an interrupt, and the kernel module makes a call into user space to inform the user space of the availability of different kinds of data or different kinds of events. There are three kinds of events which are of interest. One is the stats information, stats notification. Two is start of frame notification. You would see this as the specific processing in a routine called ISP hardware pros subdev event. This is present in isp_hardware.c file. Now once the data is generated for the stats, it passes the data and notifies the 3A module about the stats data availability. Similarly, when it gets a SOF is nothing but start of frame notification, it generates a bus event back to MCT, which will send this event to all the modules, and the modules could do specific processing based on the start of frame event notification. The third kind of processing, which is a third kind of event that is probably more important here, is the data event. The data event comes as ISP event buff divert, which indicates the availability of an output data from ISP. Now let's look at this routine to see what it really does. So the most important aspect about getting a buff divert event is to send the data to the next module, and this happens through the standard mechanism available in Camera 2 architecture, where it sends a ISP hardware notify buff divert event. This would go to the next port which is connected to ISP. This could be a pproc port, or this could be an image processing block which gets the data from ISP. That particular block, based on the buffer type. So it would get an information also regarding the kind of buffer that it's generating. It could be an AT buffer or it could be a HAL buffer. It gets the buffer and it would do the processing according to the buffer type. That completes the main processing within ISP. So we talked about starting from ISP module init to session init to stream configuration, all the way to stream on, where the bulk of the processing happens. And at this point, after stream on is complete, ISP is up and running and generating data, and the output comes as a notification, as a buff divert notification to ISP, which invokes the next module, connected modules, to pass the data it generates. Let's spend a few minutes understanding the threading module within ISP. Now, as we talked at the very beginning, ISP has session-specific threads. So whenever a session init happens, ISP creates a session-specific thread, and any event that comes to ISP for the specific session is passed on as a message to the session-specific thread, and the handling happens in the thread context. Beyond the session-specific thread, ISP also has 3 threads for each instance of ISP. There is each instance of the VFE hardware. In some of the chipsets like 8974, there are 2 instances of VFE hardware. Now these threads manage polling, in the sense it checks from the low-level hardware driver about the different events that it generates. So that's one thread for the polling. This is a second thread which deals with the update of the hardware. For example, when we looked at the ISP stream on configuration, there's a bunch of configuration which goes down to the hardware. Now this configuration do not happen from the session thread, but rather happens from a separate thread called a hardware update thread. And the third thread involves manages the stream specific configurations. This thread is present in the existing software, and there could be some optimization in this thread in the future versions of the software. On ISP debugging, there are a few things that a few macros that you could enable, which would help debugging the ISP configurations and the ISP outputs. Let's look at a part of the code which will allow you to configure these debug points. The most important aspect, or what you would be always interested in, is whether ISP is generating an output data, and if there is a corruption in the output data, because in a typical image capture or a preview or say video pipeline, there would be several modules connected to each other, and you want to figure out whether the output that ISP generates is correct or not. The best place to tap ISP output is in this routine. So the routine called ISP channel util buff divert notify. This is present in ISP channel util.c file. This routine gets invoked when the buff divert notify event comes from the kernel. And there is a dump routine inside this function. If you scroll down this function, you would find a routine called ISP channel util dump frame. This is protected with a macro ISP image dump enable. So you need to check in your configuration if this macro is enabled, and if this macro is enabled, there are certain configurations that you could do and to enable different kinds of dumping. There is an ISP property, there's an Android, there's a property called bursted camera ISP dump. Now you could configure ISP to dump a preview stream or a snapshot stream or a video stream based on this configuration. If the value is set to 2, it would dump the preview frames. If the value is set to 8, it would set a video stream, a snapshot stream, and if the value is set to 16, it would set a video stream. So you have to set the bit number, so you could OR with all three, 2, 4, 2, 8, 16, to have all three dumps together. The other debug point is typically the hardware configurations. If the ISP's AXI configuration is alright, the best place to tap into this is in the kernel module. If you go to the ISP's kernel module, there is a dump routine msp8974 util.c, which will allow you to dump the specific hardware configuration of ISP. This could be used, for example, you have a working version and a non-working version. It's always good to compare the AXI dumps of a working and a non-working version to check what has changed. But note, dumping is enabled from the kernel, so you need to go to the kernel routine and enable the dump macro in the specific places. The third aspect is, for example, when the sensor that you're working with generates more than image data. Say, for example, it generates metadata required for let's say an HDR configuration. Now ISP does process the data, and as part of buff divert notify, it would get the data for this meta streams as well. So if we go back to that routine, ISP channel util.c, we could find a conditional checks for the different kinds of stream, whether it's a meta streams that is coming from the sensor, or it is the buff divert stream that is generated by the ISP. Now you could tap into or write a routine to dump the specific streams and compare to check where the issues are. Yeah, this is one instance where you would find it is looking for the CAM metadata stream. At this point there is no specific processing, but if you'd like to add a specific processing, this would be the right place. The other topics the things to look for is the zoom configuration. We talked about the zoom configuration as part of the session init, where it configures the various zoom steps and the zoom table required for ISP. The second aspect could be checking the dual VFE scenario, as we touched upon during the stream the stream config. The stream config passes ISP with information regarding whether it's a single VFE or a dual VFE. ISP itself do not make a decision. It is done by ispif resource manager, and the configuration regarding single or dual VFE comes to ISP. The buffer management of ISP is abstracted out in a different file called buff manager within ISP. So if you have to handle specific issues regarding number of buffers allocated, whether the buffers are allocated by HAL or the buffers are allocated by ISP, the buff management routine or the specific file could be the best place to look for the debug. I hope we have covered the main parts regarding the ISP software module processing. There are a lot more to cover in terms of what really happens in the various threads, what happens during each configurations, what happens during buff divert event, and so on. This presentation or this tutorial is expected to be as a starter module to get you started on the ISP module. Go back to the source code. The best place to look for the source code is under camera 2, go to media controller folder. Under that you would find modules, and there are two folders. One is ISP and one is iFace. This is ISP interface module source code, and ISP contains the ISP specific source code out here. And you could you could insert debug points or debug macros at specific points of the processing. The main routines are covered in this tutorial, as we touched upon in the module init to session init to stream on and the stream configurations. And most of the times debug could start from these specific modules and go on to the low level details as per the debug requirement. Thank you, and I hope this was a useful session for all of you.